are talking about area of a polar region. So we've talked about area under a curve, and that's the area between the curve and the x-axis, and we've done that with functions. And now we're talking about polar regions, which may or may not be functions, and we're trying to find the area enclosed within a piece or an entire polar graph. So what we're going to do is we're going to use this formula right here, that the area of a sector is 1/2 the radius squared times theta, except, let's go down here, when we actually work it out, because we're summing this up and adding it up, the area of the polar region is 1/2, sorry, the definite integral from a to b, whatever your bounds are, of 1/2 times the radius squared d theta. So this last statement is definitely true. The hardest part of finding the area is actually finding the limits of integration. So let's go ahead and let's look at example 1. Now I'm going to write 2 theorems up on the board. So we are going to need to use these. That sine squared theta is equivalent to 1 minus cosine 2 theta over 2. And cosine squared theta is equal to 1 plus cosine 2 theta over 2. Those are things that you need to know, and those are what you're going to have to use anytime you have to find an area by hand. If you've got the graphing calculator, you can just plug it in and get a number, get an answer, but with I will ask you to do these without a graphing calculator, and you're going to have to use those 2 rules. So let's go ahead and start with example 1. So looking at example 1, I take a divided by b, so 2 divided by 2 is 1, which means we have a cardioid. Except I can't spell cardioid. So my graph is going to cross here, cross here, cross, looks like here, and something like, I missed that, over there. Okay, so on my x-axis is not exact, but we're going to go with close enough. So the next thing I need to know is, well, what, if I were to graph this, what thetas would I need to make one full cardioid? And for the cardioid, we need to go from 0 to 2 pi to get the entire graph. So because we want the area bounded by the whole graph, we're good with our bounds. Our bounds need to start at 0 and go all the way to 2 pi. That would give me this entire graph. So my area is just going to be the definite integral from 0 to 2 pi of 1/2 my radius squared d theta. So there you go. There's your new calculus, is just that part right there. That's all. And again, if you had a graphing calculator for this kind of a question, you would simply plug it in, get an answer. However, we're going to go ahead and work this one out by hand. So first thing I need to do is actually square this thing out, which doesn't look like it's going to fit over there. So this is going to get kind of squished, so I apologize. So we're going to come, sorry about that. We're going to come over here, and we're going to have 1/2 integral from 0 to 2 pi of, when I square that out, I'm going to get 4 plus 8 sine theta plus 4 sine squared theta, d theta. And now I'm going to find the antiderivative term by term. At this point, though, I do notice that I have a 4 sort of everywhere, and I have a 1/2 out front. So I'm actually going to factor a 2 out that's going to balance with my 1/2 in the front so that I don't have a 1/2 anymore. So this is going to be the integral from 0 to 2 pi of 2 plus 4 sine theta plus 2 sine squared theta d theta. So at this point, I'm ready to take an antiderivative, and I look at each term. Can I take the antiderivative of 2? Yes, that's going to be 2 theta. Take the antiderivative of 4 sine theta? Yeah, that's going to be a negative cosine something or other. However, this is troublesome right here. I cannot take the antiderivative of sine squared theta, which is why I'm going to use the first rule that I wrote down at the top. So I'm going to replace my sine squared theta with 1 minus cosine 2 theta divided by 2. So let's rewrite this again. So I have 2 times 1 minus cosine 2 theta divided by 2 And at this point, the 2 in the front and the 2 in the denominator actually reduce out. So when those things reduce out and I combine my like terms, because now my like terms would be this one is going to combine with this 2. So I'll rewrite it one more time before I take my antiderivative. So now I've got 3 plus 4 sine theta minus cosine of 2 theta. And now I'm ready to take my antiderivative. So I take my antiderivative, that gives me 3 theta minus 4 cosine theta minus 1/2 sine 2 theta. And my bounds are 0 to 2 pi. And now I'm just going to plug in my bounds, subtract, and simplify. So I have 3 times 2 pi minus 4 cosine of 2 pi minus 1/2 sine of 4 pi minus 0 minus 4 cosine of 0 minus 1/2 of sine of 0. And now I need to come back and realize to use my unit circle information to get a final answer. So of course 3 times 2 pi is 6 pi. And then cosine of 2 pi is going to be, sorry, real fast, cosine looks like this. So cosine of 2 pi is 1. So it's going to be subtract 4. And then sine of 4 pi, real quick graph of my sine. Sine of 2 pi is going to be 0, so sine of 4 pi is also 0. So that's minus 0, plus 4 cosine of 0, which is 1. And then plus 1/2 sine of 0, which is 0. So my negative 4, my positive 4 cancel out, and I'm left with 6 pi. So the difficult part is not the setup typically. The bounds can be tricky to get, and then the work involved by hand can be tricky. So let's go ahead and look at example 2. So for example 2, I have a rose. So I know that this is going to be a rose. I know that this thing right here is odd, which tells me I need to go from 0 to 2 pi, 0 to pi. If it was even, it would be 0 to 2 pi. We have 3 petals, and we know that we are going symmetric to the y-axis. Okay, so this is all our information about our graph. So I'm going to go ahead and get symmetric to the y-axis. Sorry, the length of the petals is 2. I didn't write that down. That's terrible. I apologize. So here's my rose, terribly drawn. So next thing I need to know is I've got 3 petals. I'm symmetric to the y-axis. What are my bounds going to be for 1 petal? Because I only want to find the area of 1 petal. I don't want to find the whole thing. So what I'm going to have to do is figure out, well, to get 1 petal, what do my bounds have to be? Well, to get the whole thing, I'm 0 to pi, which means to get 1 petal, I should be 0 to pi over 3. Because if I go all the way to pi, I get 3 petals. So now we can set up our area. So what I'd like you to do right now is go ahead and write down your setup for the area for this particular problem. So my area is 1/2 definite integral from 0 to pi over 3 of 2 sine 3 theta squared d theta. And of course, to actually work this out by hand, I'm going to need to square that out, change into using my sine squared formula again, and then working out plugging my bound, subtracting, and my unit circle. So what I'd like you to do right now is go ahead and pause the video and work this problem out by hand. So go ahead and please pause the video now. Here is my solution in blue. So if you did not get pi over 3, please pause the video now and find out where your mistake was. If you are good, we are on example 3. So example 3, we've got a rose. Again, we're trying to find the area of one petal. So first thing that I would like for you to do right now is go ahead and sketch the graph of this particular curve. So go ahead, pause the video now. So here's my graph. We have 4 petals. We have even cosine of 2 pi. The 2 pi is even, so we need to go from 0 to 2 pi to create the full rose. We have 4 petals, and we're symmetric to the x-axis. Now this one's a little more tricky because of the nature of the direction of this one. In creating this, it's not as simple as just going, okay, so 0 to 2 pi gives me 1 full rose, I have 4 petals, and I divide by 4. That doesn't work with this one. So what I need to do is I need to figure out, well, where is this thing equal to 0? So 4 cosine of 2 theta, where is that equal to 0? Because this has to be the starting point of any petal, has to be at 0, 0. So I want to know when that is equal to 0. Well, that's when cosine of 2 theta is equal to 0. And cosine is equal to 0 at pi over 2 and 3 pi over 2. Hold on a second. Coming back up to my little sketch, here's my cosine graph. This is 2 pi over here, which means this is pi, which means right here is pi over 2, and this is 3 pi over 2. So cosine is 0 when I'm taking the cosine of pi over 2, when I'm taking the cosine of 3 pi over 2. So, sorry about that. Coming back down here, I know I want 2 theta to be pi over 2, and I also want 2 theta to be equal to 3 pi over 2. So in the first one, that tells me that theta is going to be pi over 4, and in this one it tells me theta is going to be 3 pi over 4. Now, at the same time, I could have actually used the bounds from negative pi over 4 to positive pi over 4. That's also going to give me a single petal. I'm going to go ahead and just use the pi over 4 to 3 pi over 4. It doesn't matter. But once you know that the pi over 4s are where the zeros are, you can pick any two that you would like. So what I'd like for you to do right now is go ahead and set up the calculus for finding this area. Go ahead and pause the video now, please, and write your setup. Here is my setup in black. So what I would like for you to do now is also pause the video and work this out. I believe the answer is 2 pi. So go ahead and pause the video now, please. Here is my solution to example 3. So go ahead and pause the video if you did not get 2 pi to figure out where your or my mistake is. Hopefully this clarifies a little bit about area for a polar region, and I hope you have a wonderful evening.